Flip Tanedo, who everyone probably knows Flip, but I'm just going to briefly introduce him. So Flip has actually won many awards and scholarships and fellowships. So I'm just going to briefly mention some. They include the Goldwater Scholarship, the Marshall Scholarship, the NSF Research Fellowship, the Ford Foundation Fellowship, the Soros Fellowship, and the UCI Chancellor's Advanced Postdoctoral Fellowship. After coming to UCR from Cornell, where he got his PhD, he's continued this sort of trend, and he's won the UCR Graduate Division Commitment to Graduate Diversity Award, the Hellman Fellowship, the UCR Junior Faculty Excellence in Teaching Award, and as well as the impressive National Science Foundation Career Award, very prestigious. So happy to have Flip today to talk to us, and he's going to tell us about dark matter and various ideas about dark matter. So Flip.
All right, thank you very much, John, and welcome everybody to another unique but slightly more in-person quarter. All right, so at some point, most of the people in this room have heard zillions of introductions to dark matter. So I would like to start by assuming that dark matter is real. And by that, I mean that there are observations that seem to point to the existence of some new fields in our theory. So let me eschew any type of experimental motivation for why we know this is true. And instead, let me focus on what it means to have a theory of dark matter. So this is what I spend my time thinking about. And contrary to colloquial belief, it's not the Wild West when we talk about theories of dark matter. You can't just make anything up. Any good theory of dark matter tells you what it is, how it got here, why it's still here, so stability, why we have not discovered what its particle nature is, and how we will discover it. So this game, this puzzle is actually remarkably constrained. So I'd like to start with a morality tale. I don't know if many people know about Urbain Le Verrier. So Urbain Le Verrier was, I don't know what you would call him. He was a mathematician, a physicist, astronomer, back in the time when they were all kind of the same thing. And he looked at tables of data as an observer would do, and noticed that from these tables of the positions of various planets, that based on Newtonian mechanics, things weren't quite right. And Urbain Le Verrier predicted that there should be another planet sourcing the missing gravity to explain his observations, or to explain other people's observations. And here is a picture. Le Verrier made a prediction that the planet that we now know as Neptune is here. And his competitor, who is English, Adams, I suppose, made a prediction over here. And this is why we say Urbain Le Verrier was the first person to discover quote unquote dark matter, in the sense where observations from astronomy told us that there is something missing. And usually when I present this, I say, how many people here know about the discovery of Neptune? And all of the astronomers will nod and say, oh yes, we learned this in Astronomy 101. And the particle physicists will say, what is a Neptune? Now,
there's more to that story that you have to include. And that is, he went 20 years later, he took the same kind of discrepancy for Mercury.
Now, Barry, are you about to say what I want to say? Are you about to tell this story? Is this the story that you were?
Yeah, go ahead.
All right. So as Barry was just nudging me along, there is a second part to this story. The second part is that Le Verrier was very proud of himself. And when there was another astronomical puzzle, and this puzzle is the precession of the perihelion of Mercury. So all of the graduate students here who took GR with me or with Simeon know exactly where this is going. Le Verrier said, I know exactly how this game works. There's another planet, and the best fit is that there is a planet, I'm going to name it Vulcan. And this is actually a map from some map maker in New York from 1846, predicting or establishing the orbit of Vulcan. And so most of us know that the way that this puzzle played out is actually quite different. And so one theme that I would like, especially the students in the room, to think about is this idea of evolution versus revolution. And oftentimes progress in physics requires both. But what's probably a bit more subtle is progress often involves very bold evolution and sometimes very modest revolution. Okay. So with that, I want to go back to what exactly is it that you do as a particle physicist thinking about dark matter, or really a particle physicist think about anything as a theoretical particle physicist. And usually you start with this idea of having a puzzle, and that puzzle is always subject to everything else we know about the universe. So all past observations. And usually what comes along with the puzzle, any good puzzle is a puzzle because your model for the universe does not simultaneously fit the puzzle and the data. So what do you do? So the way it usually works, the way it always works for me, is that you make a hack. You figure out what it is about your model, your theory, that really makes this puzzle incompatible with prior data. And this is not a trivial thing, right? Your observations are actual measurements of things. Your theory is a Lagrangian, an effective Hamiltonian. How you actually connect the observations and different types of observations to a theory to determine that something is not compatible, and then how you hack the theory to make the theory compatible is actually a very non-trivial thing. And as you can see in this picture, that tends to be very inelegant. Sometimes you break things. You actually have to jam something into your theory and hammer it in. You have to drill holes, and maybe it's a little bit rickety, but you learn something from doing that. And then after that, you can think about building a new model, a top-down model, a UV model that explains not only the puzzle and the prior data, but then goes on to make predictions to tell experimentalists and tell your observer colleagues, if this new model is actually correct, or if there are features about this that are correct, then we predict some other observations. All right, so that's my retelling of the scientific method. I say that because I've had so many freshmen knock on my door this past week saying, so you're a theorist, don't you just sit in your chair and drink wine and listen to music and come up with stuff? And there's actually a whole process here. So what I would like to tell you is these are the ways that a theoretical physicist earns their stripes in phenomenology. You can either be the one to interpret data with respect to theory. You can frame anomalies with respect to features in a model. So turn experimental question marks into theoretical question marks. Or you could be the one building models that complete these features and make new predictions. And in this talk, I want to tell you 3 brief stories for each of those parts of the process. All right, so that is my, so for those of you, John gave this very charming introduction, but for those of you who don't know me, over the course of the next 45 minutes or so, you will know me. The first story I'd like to tell is about neutron stars. So neutron stars, in the back of my mind, look like this. They're balls, they're heavy, they're about the mass of the sun, and they're compact, they're 10 kilometers in radius. And the story about neutron stars that I want to tell will relate to how do we make sure that we are getting the most out of our data to interpret our theories. Okay, there is a favorite way, my favorite way to discover dark matter. There are many ways to search for dark matter, but there is one way that will be so elegant and so clean and was built exactly to search for dark matter, and that's direct detection. And the idea is you could have a dark matter particle come in, you can exchange some kind of force mediator and bounce off of a nucleus, just recoils off of a nucleus, and the energy of that nuclear recoil could be detected. Right now, our most powerful experiments are basically vats of xenon. And you should think, why is xenon a good nucleus to recoil off of? And for the graduate students here, I can refer back to my 2019 colloquium, which is recorded. But our favorite nucleus is xenon, and we can search for what happens when you jiggle a xenon nucleus in a large vat of xenon. This class of search has been incredibly powerful. So we see plots like this. These are direct detection reach plots. On the x-axis is the mass of dark matter. So in GeV, 1 GeV is the mass of the proton, and yes, a few orders of magnitude in the x-axis. And on the y-axis is the scattering cross-section, which you can think of as the general strength of the interaction. Oh gosh, Alec, be careful. He was standing on the desk. So these plots, these lines here correspond to different direct detection experiments. And this region in pink has been experimentally excluded up to a handful of caveats, which we don't need to get into. But this is territory that's been explored. So for dark matter, that's 100 GeV, 100 times the proton mass. This strength of interaction with nuclei has been experimentally explored. Down here, you see this blue region, which is neutrino coherent scattering. This is the point where neutrinos from the sun give you an irreducible background and make your search much more difficult. But as a rough approximation, this is what is known and this is what is unknown, and this is where it gets challenging. And when these two regions overlap, the search becomes much more difficult. And in the spirit of asking, how do we know, how are we getting the most out of our data? We could ask, what would it take to make this picture better, to make this reach stronger, to make this program more sensitive? And one way is to have more targets. If you have larger detectors, denser material, more nuclei. Another way, which is a little bit more subtle, is to have faster dark matter. Dark matter in the galaxy is actually remarkably slow. And the speed at which dark matter interacts with a nucleus actually affects the type of recoil that you get due to the kinematics of the type of interaction. So for example, if we have an interaction mediated by a pseudoscalar operator, these things tend to be momentum dependent. Finally, it would be nice if we could get away from this solar neutrino background. And so when we're just saying wishy-washy things like this, you could just imagine maybe we just take direct detection experiments and put them in space. And putting things in space, of course, have all sorts of practical issues, not the least of which is cost. How do you get a coax cable all the way to wherever you're going to put this direct detection experiment? And oh yeah, what type of laboratory is going to house this direct detection experiment? And propose, while other people have proposed, that a budget option is to use neutron stars. So again, this is a neutron star. The mass is not to scale, the mass is about the mass of the sun. And it is about the size, the scale of Riverside County. So there we are. So if I put the mouse over here, that's overlapping Alec. The thing about neutron stars is compared to a vat of xenon, they are indeed large volume. There's tons of nuclei, well, tons of neutrons. They accelerate dark matter because they are dense and heavy. They gravitationally accelerate dark matter. And for the cognoscenti in the room, there are no ceilings and no floors. And what I mean by that is there's no neutrino background, meaning there's no floor here coming from a background of neutrinos. And there's no overburden. So one of the problems of features of xenon-based searches terrestrially is we tend to put these things underground to avoid background from radiation from the atmosphere. But you could have models of dark matter that are super strongly interacting that never make it to these detectors. And that's one of these weird pockets of where you can hide a theory, but you don't have that in a neutron star. So the proposal from some colleagues not too long ago was that dark matter could be accelerated by a neutron star and could hit the neutrons in exactly the same way that they would hit xenon nuclei. And they would cause the neutrons to recoil, and they would deposit their kinetic energy onto the neutron star. That kinetic energy goes towards heating the star, and we can predict this increase in temperature. And the hope is that you would even observe this at upcoming telescopes like the James Webb. And the way it would work is that we would want to have a sufficiently old neutron star. So we understand how neutron stars work more or less with known physics. And if there were a sufficiently old neutron star around a gigayear, these neutron stars have their own cooling mechanisms, and we expect them to be around 100 Kelvin. That is the temperature of Hoth, right? And this is, are these wampas? I think these are wampas. Yeah, is that what a wampa is? If, however, there was this flux of dark matter scattering on neutron stars, depositing their kinetic energy, then for plausible ranges of interaction strength, the neutron star would actually be closer to 1600 Kelvin. That is actually pretty close to the temperature of Mustafar, where Darth Vader went to exile. And the name of the game, experimentally, observationally, is first we would have to find a sufficiently nearby, sufficiently old neutron star. And that's something that we would hope to find using something like FAST. The expectation is there's maybe around 100 old neutron stars within 50 parsecs. And that's something we can quibble about, but that's the assumption, that's the hope. And then with something like the James Webb Observatory, you could use this is something to search for exoplanets. You could use the James Webb to measure the temperature of the neutron star. And this is an estimate for how long it would take. So 10 to the 3 seconds is around 15 minutes. So we're talking about a few hours of observing time to measure the temperature well enough to observe a difference from 100 Kelvin. And when we got into this game, the first thing that we did was, we wanted to compare how good this search was compared to ordinary direct detection. And so this is a type of plot that we make for a certain class of interaction. So there's many different types of interactions. Question from Kiro. Kirill, your hand.
Sorry, yeah, I was muted. So one question. So it seems to me that you need 2 data points. So you basically have a theory for what the temperature should look like as a function of the age, without and with with this interaction with the dark matter. But how do you know the age independently? I mean, you're just looking at the star. You see the temperature, and what does it tell you? You don't know whether it's a heated old star or whether the star is just sufficiently young.
Yeah, so this, I apologize, I'm going to leave the details to our astronomy colleagues, but this is something from the radio pulses of the neutron star. I think these neutron stars, as they cool down, this is them spinning down, right? I think. From the radio pulses, you have a measure of the age of the neutron star. So you can say this is a neutron star that is sufficiently old where it is worth measuring the temperature. So that's the first step. Then the second step is, now let me dedicate telescope time to actually measure that temperature.
All right.
I'm totally open to any of our astronomer colleagues telling me that I'm an idiot. It wouldn't be the first time. All right.
You're correct.
Thank you, Gabby. So this is just for one type of interaction, which looks like this in a Lagrangian. Yes, question from Umar. And Umar has to unmute. Is there a question from Umar?
Don't you have an angle? You'll have an angular momentum transfer to the neutron star too, won't you?
Yes.
And wouldn't that cause?
Sorry, you're asking about dark matter imparting, the dark matter be imparting angular momentum onto the neutron star.
Yeah.
Yes. Good. So we are assuming isotropic dark matter. So to good approximation, the dark matter is in a non-relativistic cloud around the neutron star. Most of the momentum that the dark matter picks up is from the gravitational pull of the neutron star. So this is roughly isotropic. But you're right, this is something where if there would be some additional rotation, this is not something that's been investigated.
If it is spinning around a black hole or something, it has a net angular momentum, won't it? The dark matter?
So we're looking at in our neighborhood. We're talking about within 50 parsecs.
Mm-hmm.
All right, good questions. So long story short, these solid lines here are various types of terrestrial experiments. On this plot, the x-axis is again the dark matter mass. The y-axis is now the inverse coupling. It's a dimensional coupling. So higher is more sensitive. And what we found is that for a large swath of dark matter masses and for different types of operators, this type of search is actually as sensitive or more sensitive than current or projected experiments. Okay, so that's pretty neat. This thing that people were thinking about is actually a key point in complementary searches for dark matter. And there's a reason, so you can think about the behavior. So we were curious, like, how does this thing actually work? And for some intermediate range of masses, the story works exactly as I told you. But the search kind of peters out at low masses, because at low masses, when even the accelerated dark matter, when it captures, does not impart enough momentum to scatter off of the degenerate targets, right? The degenerate neutrons have a Fermi surface, and if you can't impart enough momentum to pop the neutrons off of that Fermi surface, that scattering is phase-space suppressed. So you have Pauli blocking that kills off your search for very low masses. And for very high masses, you don't impart enough momentum to capture, and so you have to scatter multiple times, which weakens your search. Okay. So that much is a cute story, and now we understand how the story works. And we thought that's really cool. At around the same time, the dark matter community has been getting really excited about leptophilic dark matter. That's dark matter that prefers to interact with electrons and its cousins. And part of the reason for this is that dark matter with lepton couplings are one way of searching for low mass dark matter. And another reason is that this is just a very obvious way to avoid nuclear recoil. If we haven't seen any nuclear recoils, maybe it's because the dark matter is talking to things that aren't nuclear. So maybe leptons. And we were thinking about, this would be something interesting to think about for neutron stars, because our very simple model of a neutron star being a ball of neutrons is actually a little naive. And for this problem, it is worth evolving that picture, this model, and including the electrons, which is something that nuclear scientists have all done. And we quickly realized that this is actually a very challenging puzzle. And the reason why this is a challenging puzzle is because the degenerate electrons in a neutron star are also relativistic. That means rather than being stationary in the lab frame, the electrons have large momenta relative to, in different directions relative to the incoming dark matter. And in order to do this calculation properly, there needs to be a large boost that you do for every single interaction. And so our postdoc, Anneke Jaglikar, said, well, you know what, that's a challenging problem, but I can do it. And he wrote this fantastic Monte Carlo code. But to do that, we had to really understand the underlying physics. So let me say it in a different way. This is something which is very different from the LHC. For a stationary, non-relativistic target, dark matter sees a bunch of non-moving neutrons, and they all have the same roughly geometric cross-section, shown here in blue. This is a cute picture from Anneke. When you have relative degenerate targets that are zipping all over the place, right? They have non-zero energy, a non-zero kinetic energy. They have different orientations relative to the dark matter. And they have different relative energies, right? Different center of mass frames, and therefore they have different effective cross sections. And so when you want to figure out what is the cross section that you're probing, there are actually literally many different cross sections. To say it differently, this is now the phase space or the momentum space of the target. For a non-relativistic target, there is this purple skin where a target neutron can be scattered, can scatter with dark matter. And if the momentum of the target neutron is too small, you're Pauli blocked, right? It needs to pop out of the Fermi sea, pop out of the Fermi surface. But you're limited by how much energy the dark matter can impart. When you have a whole bunch of electrons moving in different directions, the relative direction of the electron matters. So if the electron is moving head on to the dark matter, you can transfer a lot of momentum. And that electron has more of a chance to pop out of the Fermi surface. If the electron is moving collinearly with the dark matter when it scatters, you don't transfer a lot of momentum, and it's unlikely to pop out of the Fermi surface. So you lose a lot of symmetry in the phase space for this problem. Okay, so now I just want to show that this is getting challenging. So we're able to do this, and I just want to put the result forward before talking about the physics, because the result is actually surprisingly amazing. The result is that there is an order of magnitude improvement, well, 2 orders of magnitude improvement compared to what you would expect if you approximated electrons as non-relativistic, as some of our colleagues had previously been doing. So this dotted line here is a non-relativistic approximation, and this blue line is what you get from electrons. Again, the y-axis is the sensitivity, so higher is more sensitive, higher is better. The shaded region over here, these are the electron scattering direct detection experiments that are terrestrial that the particle physics community is really excited about. And what this tells you is the observation of a single neutron star that's sufficiently old and sufficiently nearby gives us a lot of data. This is a key piece in the landscape of understanding electron recoil. Kirill, what's up?
Yeah, sorry, just a question about neutron stars that you may or may not know the answer. But do I understand correctly, if they have electrons, they are actually macroscopically charged? Or is there some neutralizing charge, protons or something else inside?
Good.
I mean, because if they were charged, I can't imagine what would keep electrons there, actually. Coulomb force.
There are also protons.
All right.
Good.
And
Thank you.
What do you know about their relative concentration to the neutron matter? Because like whatever gains you make of the cross section may be completely killed by if the relative concentration to neutrons is very small.
Ah, good. So that is absolutely included in this. Good. So when we talk about these approximations, it's not that we're saying, oh, let's replace every neutron with an electron. That would be completely naive. The nuclear scientists, as if this is some vague class of people, there are actually off-the-shelf models for the distribution of electrons, protons, hyperons, muons, electrons in nuclear matter. So this is something that we're taking off the shelf. Good, but that's exactly the correct thing. And that's actually what we've been arguing about with some of our colleagues in this search. Okay, so if we observe a neutron star that's hot, that's nearby and it's old, that would give us a line on this thing, and it would give us a target, right? All of this is just to say that this landscape of different experiments, they piece together in ways that are really very surprising. And the other thing which is really neat is as we dug through this, we found different scaling behavior for the case of relativistic targets. Now, this is all specialized to the case of neutron stars, but the formalism that we developed is completely general for scattering. Now, off the top of my head, I couldn't figure out what else this is good for, but this is a fixed target experiment with quantum degenerate matter that is relativistic. And we found that previously the scaling depended on the mass of the target. That ends up being replaced by the Fermi energy for reasons that are actually not completely obvious. And we ended up charting out the phase space of properties of hypothetical targets with hypothetical dark matter masses. So this is just to say that you can have a target that is very light compared to the Fermi momentum. So this is like the electron, or a target that's very heavy compared to the Fermi momentum, like a neutron. And the way that these curves, so this is a cartoon for what all of these reach plots look like. The way that these curves behave can actually be predicted from simple scaling laws that you get from looking at this really ugly calculation, but using dimensional analysis. So those of you in the 231 class, the reason why we do 3 days of dimensional analysis is precisely because this is how we think about physics. So there's a regime here where dark matter captures after one scatter. There's a regime both for the heavy and the light guys, which actually divides into subdivisions, where Pauli blocking becomes a big effect. The fact that the quantum degeneracy, it can phase space suppress your scattering. And there's a regime where the particle, even if it is low mass relative to the Fermi energy, even when the target is low mass compared to the Fermi energy, that the dark matter is so heavy that it requires multiple scatters to capture. So this middle regions where you're most effective. The side regions are where your search peters off. And actually, I say this very glibly, as if every plot looks like a little plateau like this. But with Atomic, we really went through this very systematically and took apart the very ugly cross-section weighted by the different boost factors and went through and made these flowcharts for how you understand the scaling laws that you get coming from a Monte Carlo code to see what happens when you have these degenerate targets. And this is something which had not been done before. And people were talking about, well, what happens when you have a neutron star with this component or that component? And no one really properly understood what the curves ought to look like. And this is the first time we actually showed it. And you can see that this is for a, say, bosonic dark matter hitting a fermionic target. The scaling, actually, you can have a few different plateaus. And again, so this is now a message, again, for the 231 students, right? One of the first things we did with dimensional analysis in 231 is, how do you know when your calculation is good enough? And one of the issues that we had, so early on, we put out our work and we were very proud of it. And some of our colleagues were very skeptical. And first, they didn't quite understand how the relativistic scattering worked, and which is why we went through it very carefully. And they also didn't understand why the non-relativistic calculation is very different. And after we sorted out the scaling laws and really presented it very carefully, they were very quick to say, okay, well, let's make it even better. You know, you assumed that the neutron star is just a ball of neutrons and maybe a ball of electrons with this density. But this model we know is already very naive, and you have to take into account the temperature differences and do all these things. And doing a very sophisticated neutron star model, this is exactly what Kirill was mentioning. They actually get the same behavior that we predicted, okay, up to maybe a factor of order few for this particular operator. But this is, for me, was the validation that the Monte Carlo that we did, based on this very simple model where every physical process was understood, is actually a very robust way of understanding the actual physics. All right, so before I jump forward, I just want to say a little bit how we got here and where we're going. So the idea of working on dark matter capturing on celestial bodies was one of the first things I was playing with at UCR when a very young, precocious honors undergraduate student came to ask me if I had any computational projects. And it turned out that, so Adam and I got together and we worked on dark matter capturing in the Earth in the presence of new forces. So this is really kicking off the past 5 years of me thinking about new forces talking to dark matter. And I believe, so Ward told me that Adam's honors thesis, which was published in Computer Physics Communications, was probably the first undergraduate honors thesis at UCR in theoretical physics. So kudos to Adam, who is now my graduate student. In parallel, around the same time, Ernest Ma had a graduate student who was looking for new projects. And completely separately, we developed this model of lepton flavor violating mediators. We were thinking about collider searches. And after working with Atomic on this code, working on neutron star capture, we thought, you know, there's some really fun kinematics that we could do if we had these weird models where when you talk to an electron, you convert it into a muon. And as we were thinking about this, another precocious undergrad, this time from Stanford, Sagata Pinano, reached out to me. So Sagata and I had met at a Filipino-American mixer through the Stanford Alumni Association, where I was invited as the first Filipino-American professor of particle physics. And she said that her REU at Argonne had fallen through because of COVID, and was there something that we could work on remotely? And so here is the first preliminary plot from our computational project over the past year of doing the same thing for a model that we developed with Zaki. Okay, so that's one story about how do we get the most out of our data. That's one piece of doing phenomenology. Here is another piece. So this other piece is the Atomic Anomaly. This is what do you do when you have new data that is surprising? So this, I guess, is new forces hiding under our noses, where by noses I actually mean nuclei. This is nuclear physics. And the game that we're playing is, given an anomaly, what type of hack do you have to do? And what do you have to do to your theory? How do you quantify things at the level of, here's what your Lagrangian needs to do to be able to accommodate both the anomaly, if you interpret it as new physics, and everything else that you know about the world, the universe. Okay, so here is the Atomic Anomaly in a nutshell. This is from 2016. The Atomic is the lab. They take lithium targets and they bombard it with a monochromatic proton beam, and they excite a particular resonance of beryllium, the beryllium nucleus. And what they were looking for was internal pair conversion, IPC. And internal pair conversion is when you have a nuclear de-excitation that emits a virtual photon that goes to an electron and a positron. And they were looking at the opening angle between the electron and the positron. This is my sketch of what their detector looks like, their old detector. Those of you who have taken quantum mechanics from Haibo can calculate what the spectrum of the opening angle distribution ought to be. It depends on the quantum numbers of the excited state and what the transition looks like. So depending on whether it's an electric or magnetic transition, depending on the partial wave, you get a different distribution of opening angles of the electron and the positron, but these are all smooth distributions. In contrast, if this de-excitation occurred because you emit some new particle that is produced on shell, that means that the invariant mass of the E plus and E minus are actually fixed to be the mass of this new particle. And the kinematics are also fixed, so you have a different distribution of opening angles. Right? You should see a resonance. And this is indeed what the Atomic group published in 2016. 2016, 2015, this was a good year for anomalies. This is right around the same time as the 750 GeV anomaly at the LHC. And this was a team of particle physicists, and there's me starting my job at UCR, who we were the first ones to really do the hack, how to take this data and say, what does this mean for a Lagrangian? All right, here's what the data looks like. So they excite the lithium into an excited beryllium state, and for different energies, so these are just the rescaling is just so they're shifted in the plot. Here's the spectrum of opening angles, and you can see that there are little bumps here when you tickle the lithium lithium nucleus at just the right energy. The idea is just the right energy, so you have this de-excitation, you're getting just the right excited state. So this de-excitation allows the on-shell production of some new particle that I guess people have been calling X. And the bump disappears when you go off resonance. There are other checks that they did. They looked at what the distribution of opening angles looks like relative to different hypotheses for the mass of the on-shell particle. And they looked at the bump, they looked for the bump in the invariant mass. And the paper from this Hungarian lab at the time said 6.8 sigma for the significance. What this means is this is not statistical uncertainty. This is not statistical. Whether it is systematic is a completely different question, and depending on who you ask, it's still an open question. Our paper that characterized this anomaly in terms of what does a particle physics model have to do was actually my first press release with UCR, which you can tell because we had the old UCR logo. One more path for why this is actually an anomaly. So one, there's a bump. The two observations of the distribution of opening angles and invariant masses both point to something around 17 MeV. The bumps disappear when they're not supposed to be there. So when you're off resonance or when the energies are asymmetric. So they're consistent with the kinematics of on-shell production. And the thing that you're probably wondering is, how is it that this completely random nucleus happens to have this transition that we wouldn't have seen anywhere else? And in fact, this is a particularly large transition. And I think it's one of the largest magnetic transitions of this partial wave, where it's plausible that you wouldn't have seen this in other nuclei. Okay, so if we take this seriously, as we might as well, what can theory tell us? And this is where the fun starts. So now we go back and we go through all the chapters of Sakurai that Haibo taught us, and we want to categorize what the transition looks like according to its quantum numbers. So spin, angular momentum, and isospin. And by the way, isospin turns out to be a red herring because actual nuclei have isospin mixing. And we can use this to establish a nuclear effective theory of nuclei, beryllium nuclei, coupling to a hypothetical new particle. and then we can figure out what are the properties of that coupling. So just by doing quote unquote textbook nuclear physics coupled to a new particle, you can write down the types of interactions for the most common types of particles. So a spin 1 parity even vector, spin 1 parity odd axial vector, a scalar or a pseudoscalar. So yesterday afternoon, one of our undergrads, a senior, stopped me as I was walking by the hub and said, "Oh, are you Dr. Flip? You're giving the talk tomorrow? Is your talk going to have axions?" I'm sorry, I've forgotten your name. The person who was talking to me. I told him I apologize, my talk won't have axions. This is the closest thing to an axion in my talk. And we found that it was actually very challenging to write down a model where something like an axion or something like an axial vector could give you this decay. Now, it turns out that our clever colleagues later on found loopholes that they were able to exploit to build viable models, but we crossed these out as being kind of strained at the time. And there were big uncertainties with nuclear matrix elements. Just from the effective theory, though, we could say that you could not have this contribution from a scalar particle, dark Higgs, if you want to be trendy. The dark Higgs interaction vanishes by, if you want, gauge invariance and integration by parts, right? Just from the Lagrangian. That is something that the theory is mandating for us. And so we were left with, well, our best shot is for any hypothetical new particle to be a vector. And those of you who have listened to me talk about physics or Haibo talk about physics, or any dark matter people talking about physics, probably know what type of vector we're thinking about. We're thinking about the dark photon. And this is indeed what the experimentalists initially thought. They thought, oh, we have discovered a dark photon. Now, part of doing this theoretical physics game is trying to figure out what you know and what you don't know. And if this were a dark photon, it turns out you're ruled out like hell. And the reason why you're ruled out is because this Na48 experiment at CERN looks for dark photons from pion decays. Pions can decay into a photon and some new particle. And if there were such a dark photon, they would have seen it, and they haven't. And it's been ruled out by orders of magnitude. The figure of merit here is epsilon, which is the coupling to the ordinary matter in units of the electric coupling. And so we did the humble thing and said, well, let's break the dark photon. Let's do something which sounds very silly and just propose that maybe the coupling, it's not just one coupling, but there are 3 separate couplings. We're breaking the model. And those of you who are theorists know that you could actually do gross damage, like really bad mathematical damage to your model by doing this. But we were doing this just because we want to figure out what does it take to make this fit. We can deal with making the theory work later. And the cool thing that we found is if you really want to avoid this bound, pions going to a photon and this new particle, you could do this by mandating that the new particle does not talk to protons. And that's actually a little bit surprising. No one had ever framed it in those words before. For those of you who are taking 225, you can think about this in terms of what is the particle content of the pion? What are the things running in the loop that give you the pi to gamma gamma interaction, where this becomes gamma prime? And you can use the fact that the pion content has this minus sign. So if you pick your charges carefully, you can get the up quark loop to cancel with a down quark loop. More prosaically, you can use an effective theory where you only have mesons and protons and neutrons. So this is what Steinberger did in the 60s. And the proton is charged, so it talks to the photon. The neutron, which can run in the loop, does not talk to the photon. So if the new particle doesn't talk to the proton loop doesn't contribute. And if the neutron is there, then the photon doesn't contribute. So if the new particle does not talk to protons, which you can tune by picking its charges to quarks, then the new particle doesn't talk to pions, and this very severe bound no longer applies. So we built this toy model where you have a different proton coupling, a different neutron coupling, a different electron coupling. And by taking these ratios, you can actually cancel out nuclear uncertainties in the matrix elements, and you can fit these things to the actual observed data. So here is the proton coupling. On the y-axis is the neutron coupling. And this protophobic limit means you have to be close to 0 for the proton coupling. And the colors correspond to the decay rates, the ratio of branching ratios, which is basically set by the experiment. How many events did you see? And so now we actually have a fit for the range of possible couplings. You can do the same thing for electrons. The main constraint here is you want to make sure that the new particle decays before it leaves the detector. So this is, again, just fitting parameters. And that laid down the gauntlet. That was the model to say, okay, it's a very odd experiment. It's a very weird result. And it begs more investigation. Here is the starting point. So what's happened since then? So we have a nice paper that actually did the UV completions. So those of you who are doing particle physics, the key trick is to make sure all of your anomalies cancel. There are a lot of fun connections one could make, including the G-2, which has been in the news lately. Ongoing experiments have started carving into the parameter space. So if I project back onto the dark photon parameter space, the beryllium anomaly is this line over here, right? It's one mass, 17 MeV. And the Na64 experiment at CERN, which is still running, has carved out around half of the parameter space. So if this is still correct, if the interpretation is correct, then we're living on a slightly narrower band of possible couplings. Meanwhile, some interesting things have happened experimentally. The Atomic group has also run a similar experiment for helium nuclei, and they found a similar type of discrepancy, a bump in the opening angles. Now, helium is a completely different nucleus. The opening angles are completely different. But when you plot apples to apples and you draw contours, so here's the opening angle. On the y-axis is the mass splitting. This is the beryllium result, and this is the helium result. They both fit to the same mass proposed particle. And more recently, people have shown that they also are compatible in the size of the couplings. So it looks like there are two kind of independent observations that seem to be pointing to a new particle in nuclear decays. Now, what would be really, really nice is if there was some other lab other than this particular lab to have some sort of cross-check of these experiments. So this is an ongoing, really curious story. Last week, there was just a conference on this in Italy. And those of you who are interested can peek at the slides. So that was early on in my UCR career. And this idea really led to playing with new forces. And my first grad student, Ian, and I, the first paper we wrote together was vector self-interacting dark matter. So playing with a weird model of new forces where spin one particles themselves interacted through a dark photon. And this was brand new because it's like the force particle itself is kind of the dark matter as well. And we did this, and Ian has since become an expert on spontaneous symmetry breaking and doing symmetry breaking patterns. And we did this, I should mention, largely because Haibo mentioned in passing that this probably was not possible. So this is Ian saying, Haibo, I can do it. A little bit later, Lexi and I worked with a postdoc in Brazil, Sylvain, and examined what would happen when you have spin-dependent forces in nuclear experiments coming from more exotic types of forces. And these include things, for example, where you don't exchange one particle, but you exchange a pair of particles. These are quantum forces. Or more exotic types of forces that aren't described by a single four-dimensional particle, but by the exchange of something more like scale invariant Mach, which is something I'm going to get into very shortly. Lexi has since gone on to write a whole bunch of really cool papers. One of them includes extrapolating the quantum force to determining the Majorana or Dirac nature of neutrinos. I'd be remiss if I didn't also mention one more junior member, visiting member of my team. I had another refugee from COVID. So this is Anaga Satish. She was a senior at Redlands High School. And when she was a junior, she reached out to me again, like Sagata saying, I know COVID's going on and maybe we could do something remotely, but I'd really like to learn something about particle physics. Do you have a computational project that I think that I could latch on to? And with primary mentorship from Adam, we are now preparing a really neat paper on new forces, so B-L forces, looking for new forces by using this picture of the sun. So this is a picture of the sun taken from Super K. Super K is a neutrino detector. And this is a photo, neutrino graph, where these are neutrino events where you look at the sun at nighttime. So these are neutrinos passing through the Earth. And the fact that you can see the sun actually constrains the existence of new forces that neutrinos would feel, because the magnetic field of the sun would bend these neutrinos and smear out this photograph. So Annika is now at Caltech doing her freshman year as we prepare this manuscript. All right, one last one, warped dark sectors. So warped dark sectors are my attempt to do really fun and insightful model building. So a warped dark sector is something which many of you have heard in the 2000s. It's the idea that maybe matter can be described in 5 dimensions, and not just any 5-dimensional theory, but a particularly weird 5-dimensional theory where you have this warped metric. So this is called anti-de Sitter space. Why would anyone ever care about this really weird, perverse GR setup? And you might wonder, hey, is this evolution of ideas, or is this some like just trying to be revolutionary for the sake of being revolutionary? So in fact, I have this nice quote here from Lenin, who was a revolutionary, who was actually against the idea of extra dimensions, I learned very recently. So why would we care about extra dimensions? So the poor answer is, there are theories of quantum gravity that require extra dimensions to be anomaly free. Okay, that's a very low level answer. The better answer is the reason why we care about these weird warped extra dimensions is because of the holographic principle, or the so-called ADS, anti-de Sitter space, CFT correspondence. So CFT is a conformal field theory. This is a theory that's scale invariant. And the point is, theories in a warped extra dimension secretly encode the information mathematically of conformal theories. Okay, so why do we care about conformal theories? I don't have any conformal theories. For most of the particle physicists here, and certainly maybe some of the condensed matter physicists care about conformal theories, but most of the particle physicists here, and almost all dark matter physicists, don't have anything to say about conformal theories. Right? There is nothing conformal in the standard model. And so it sounds exotic. But we know that every single quantum field theory lies on a renormalization group flow. So this is RG evolution, so there's your evolution, between 2 conformal fixed points. This is just what Ken Wilson taught us in the 60s. Every theory is in a flow. We probe the theory at different energy scales, and you get different conformal fixed points. So really what we're doing is we're examining the types of theories that live near the endpoints of these RG flows, rather than the types of theories that live along the middle. And what's neat about them is they seem to point to very different behaviors of ordinary quantum fields, but beyond the particle limit. So is this weird and crazy? Yeah, it's weird and crazy, but it's weird and crazy because we don't have those in the standard model. The standard model behaves like particles. It is not weird and crazy because this is just a behavior field theory in the QFT that we know. So the setup that we have is maybe there's a new force, and the new force is described by something conformal or something that lives in an extra dimension. Let me just point out that there's been a lot of recent work, and we're trying to carve out our niche and carve out, push this in a really interesting direction. But not only is there a lot, but given how open this field is, it's actually fairly modest. We're actually really pushing a new boundary here of a new class of dark matter phenomenology. I put this here for the 231 students. One thing that we get, the one thing that we're doing that's really new is we're including bulk self-interactions. And what that does is it changes the analytic properties of your 2-point function. So for the 231 students, when we spend a long time talking about dispersion relations and the analytic properties of our theories, this is why. And let's get to nuts and bolts phenomenology. What does it do? So if you've ever heard Haibo give a talk, he'll talk about self-interacting dark matter, and he'll give you a long-range potential. One thing that it does, having a continuum dark sector, is you have a potential that is now no longer 1 over r with the Yukawa factor, but has a fractional power. And Ian has done some really cool work on this, showing that this fractional power actually makes a lot of sense, both in the Kaluza-Klein limit and matching it onto a full 5-dimensional calculation. And he went on to reproduce the types of phenomena that Haibo self-interacting dark matter program has done. And he's shown how this maps onto a UV model and what new things you can do with that. In parallel, let me just jump over to Lexi. Lexi has taken the complementary approach of examining what happens when you probe this sector in a time-like regime. So you're producing these states on shell. And what happens is these warped extra dimensions, you have a bunch of resonances, which is like a KK tower or Reggie trajectory. But once you take into account the self-interactions, as all of our collider colleagues know, you end up with a large bright Wigner width, and this spectrum of clean resonances merges into a continuum. This is what Higgs physicists used to call unparticles 15 years ago. And she showed in a really heroic calculation what happens if you were to produce this, this not quite particle stuff in a dark matter annihilation or in a collider. And she worked out the analytic properties and showed what happens. And what ends up happening is you end up with this long cascade that is exponentially suppressed. And there are really neat connections between how we understand the cutoffs of our theories. Okay, there's a lot to explore left. I'm just giving you an appetizer. A lot of really neat things to do with CFTs and finite temperature. And there's a killer app for that, which is exactly stellar cooling bounds. A lot of the things that we assume about new forces really change in environments where the fact that you have a continuum versus a discrete particle will give you surprising results. So this is one that I'm really excited about. With Kuntal, Paul, and Ian, we're working at the first example of a bulk scalar mediator with bulk symmetry breaking. And these are all things that Sylvain and I had kind of mapped out as a long-term research program for really novel phenomenology that, again, the point isn't, hey, look at this cool dark matter model, it's not ruled out, but let us show you let's populate the space of possible signatures to try to discover new physics. I have a couple of advertisements. So Kuntal Paul has been our resident machine learning expert. And it used to be that when we talk about anti-de Sitter space, we always show these MC Escher pictures. Okay, this is 2D ADS. Now it seems like ADS is more popular for quantum error correction codes. So quantum information science and quantum computing is really one of these big thrusts in a lot of our research priorities. And one of the big things in ADS CFT has been the idea that this duality is related to quantum error correcting codes that are the key to having viable quantum computers in the future. Now, a cute analogy, those doing machine learning, there's a cute place that ADS also shows up, which is in the relative entropy. So those doing machine learning, you know that what you want to do is there's an actual probability distribution that you want to learn, and you take successive trained probability distributions, and you want to figure out how well does your trained probability match onto the actual probability. So what you need is some notion of inner product, and that's the relative entropy, or since it's not formally a metric, it's the Kullback-Leibler divergence. It's defined this way. And when you do this, when you take a measure for how far apart are two Gaussian distributions, you actually end up getting exactly the ADS metric. So I think in 10 years, we won't be using Escher. We'll be talking about information theory when we're motivating anti-de Sitter space. One last research commercial. So, you know, this result that Lexi had about cascade decays has been sticking in my mind. And even independent of all this conformal stuff, you can think about particle models that give you lots of soft radiation. And maybe this is some way to hide dark matter annihilations. Every telescope looking for dark matter annihilations has some minimum threshold energy. But if dark matter produces high energy particles that turn into a spray of many, many, many low energy particles, it seems like you'd be completely hidden. Alternatively, any generic dark matter annihilation will produce some amount of really soft radiation. And for the most part, people have just assumed that this soft radiation is not good for anything. And one thing I'm super excited about is this may be the key to understanding supermassive black holes. So there is a puzzle with black holes. Quasars, which have large black holes powering them, we've seen these very old quasars that have large black holes powering them. But there's a puzzle because based on how we understand black hole accretion, there's no way for those black holes to have gotten so large over the age of the universe. So those of you who've taken Simeon's class, this is super Eddington accretion. And the usual story for how black holes form is that you have old stars, one of the old stars explodes, it forms a black hole, and the black hole slowly grows by eating its sister stars. One way to produce the big black holes in these old quasars is if there were a way for black holes to directly form from all of the dust of a proto-galaxy. So rather than forming stars first, all the gases directly collapses into a black hole. This is called a direct collapse black hole. And in order to do that, you just need to make sure that you have the right chemistry in the gas to prevent the gas from fragmenting and forming stars. And this is work by Priya Natarajan that I learned about at a physics workshop a couple of years ago. Priya is Anson's advisor from not too long ago. And her point was, if you had a source of radiation from nearby galaxies, maybe that would be enough to source these direct collapse black holes that could explain these old quasars. And the thing that we're working with Yash, who is co-advised with Anson, is how do we get a dark matter model? So we know that there's dark matter in these halos. Maybe the existence of these supermassive black holes could be explained by direct collapse, which was catalyzed by the annihilation products of dark matter. And this is a really neat research direction. And you will not believe how pissed off I was to find out by complete coincidence that last year, Haibo and Wei Shang were thinking about the exact same thing. So they have their own model for how to form direct collapse black holes using self-interacting dark matter. But all of you should just wait and see, because our Anson and Yash and I have a really awesome way of doing it that's way better than Haibo's. Okay, so as I wrap up, so that was just a glimpse of the type of things that I'm working on. One other thing that's going on with me this year is this decadal snow mass process. So the APS division of particles and fields every 10 years gets together and organizes a big powwow of the particle physics community to establish research priorities for the next decade. We produce reports and lead to this series of discussions that end up leading to documents that are forwarded to funding agencies and to Congress to advise on the future of particle physics. And I'm humbled to be selected to be the theory frontier, cosmic frontier liaison. And the work that I have described in this talk actually overlaps quite a lot with the working groups and the priorities established in this decadal process. So that's something that I think I'm really looking forward to. And with that, I just want to thank everyone. Sorry, I went a little bit over time. Thank you all, and here's to a good year. All right, take care. Any questions? Yeah, Haibo's giving me the huffing emoticon. We only found out we were both thinking about direct collapse black holes when we were writing a grant together.
Yeah, we should. Maybe this year we should try that. There's a competing theory, and we should submit to one of the private foundations. They like to do this. Yeah.
It's like dueling banjos.
Yes. Oh, actually, we Gabby, Laura, I think Gabby is working on the observational aspect, right? So maybe we should talk more about this.
This is really exciting. This is really good stuff. Yeah.
Yeah, Haibo promised to come to our group meetings, and I'm still waiting.
Oh, sorry. Yes, I sent an email. Yes, I think we should talk. I mean, maybe once university open more, maybe we can meet in person even. Yeah. So I'll send you an email.
Maybe Flip will come first.
Yeah.
Any other questions?
My general advice, by the way, for students is that you should ask questions during the colloquia.
No other questions? Okay. Well,
I'll make a brief comment, and it's not about science. I'm sorry, but I was very impressed with the number of people that use shelter during the pandemic. So I shied away from starting, projects with students that I've never met before. And I'm impressed that you work with so many. So kudos to you.
Thank you.
Okay, thanks, Flip. Great talk. So thank you, and we'll see everyone next week.
All right, take care, everybody.